Okay, time to start reaction mechanisms. So let's kind of take a step back and let's just kind of look at this idea of what a reaction mechanism is. So a reaction mechanism is basically saying, all right, so far we've identified, we can determine the rates at things, but we've never talked about how they actually happen. So the reaction mechanism is going to tell you the how and by what reactions or means a chemical change takes place. So this is actually looking at how things happen. So we have a bunch of different ways reactions can happen. I can have this reaction right here occur in a single step, or I can have it occur in 2 steps. It's going to form this N2O2, which forms and then is consumed. That is known as an intermediate, right? So we form that intermediate forms with oxygen, and we form product. So both of these overall are giving us the same exact reaction, right? So if I combine these two together, what we find out is these two would cancel, okay? And then I have 2NO plus O2 yields 2NO2. So 2NO plus O2 yields 2NO2. And what you'll notice is these two things are exactly the same. This one occurred in multiple steps versus that one occurring in 1. So there are a bunch of different ways these things can happen. And so in order to determine if this is valid or this is valid, we have to have a way of identifying how. We have to have a method of saying, okay, this is absolutely possible or this is not possible. These individual steps, so these individual steps of a multi-step reaction, this is known as an elementary step. Actually, it's right there. This is known as an elementary reaction. So I have 2 steps, 1 and 2 are known as elementary reactions. The reaction here is known as the overall reaction, but these elementary steps are the process by which this reaction can occur. Good. So there's something about an elementary reaction. So I'm going to kind of copy this down. I probably should have done it earlier, but that's fine. So I'm going to copy this down here, paste. Oh, just kidding. Erase this. I'm going to try this again. I'm going to copy this. There we go. When I have an elementary step, so before I said, all right, we can write a rate law, but we're not going to know unless we do experimentals. But when we're dealing with mechanisms, if I have an elementary reaction, I can actually say, all right, this is my elementary step. And because it's the individual steps, we can actually apply a rate law to it. So for my first elementary reaction, I can say the rate of reaction 1, elementary step, is equal to K1, so the equilibrium constant of that first step, times the concentration of NO squared. And it's simply the concentration of NO because I have 2 NOs there, 2 NOs, okay? So what is the rate law for the second one? So you give that a try. Again, I would pause it. Rate of step 2 is equal to the equilibrium, or I'm sorry, the rate constant of 2 times N2O2 times O2, and that's it. Again, I've got 2 NOs there. That's why it's like NO times NO to square it, okay? So these are the rate laws of these 2 individual steps because they're called elementary reaction. So moral of the story is, for an overall reaction, you cannot draw in a rate law, but you only have to get that from experimentals. But if it's elementary steps, you absolutely can and should write out the rate laws. So there are 3 things we need to see if a reaction mechanism is valid. So in order for one of these mechanisms to be valid, we need 3 things. First of all, the elementary steps must sum to overall and overall reaction. So we've already seen this. So these 2 combine together to give us this overall reaction. So we're going to say, yeah, that's fine. Step 2, we need the molecularity to be valid. So molecularity, and we'll talk about that, has to be uni or bimolecular. Uni or bimolecular, which basically means I can only have one or two things reacting in every single one of my elementary steps. If you ever have 3 things, that's not going to happen. But again, we're going to talk about it. And then finally, my experimental rate law is equal to the slowest elementary step. We call this the rate determining step, or RDS. That's the simplified term we're going to use. Okay, so that's the idea. So let's take a look at our net reaction. So we have this overall reaction. So we're going to look, this is my overall reaction, the same one we just kind of look at. If it's a one-step process, we don't actually need to add those things together because the elementary steps overall reactions equal the elementary reaction, which equals the net reaction. So in this case, if this is the overall reaction and we say it occurs in 1 step, then we're deciding if this mechanism occurs in 1 or 2 steps. Okay. Versus this other one where we know that rate 1 is equal to concentration of, actually, I'll do that later. Yeah, because we already did it. So step 1 and step 2. Can I, if I add these 2 things together, if I add these 2 rate laws together, or I'm sorry, these 2 elementary steps together, again, this cancels and we're left with 2NO plus O2 yields 2NO2. So good. So first of all, the net reaction, if it's done in 1 step, we're good. That passes the test. If it's done in 2 steps, those 2 are the same. Okay. Next thing, the molecularity. Oh yeah, sorry, let me quickly get here. This is consumed, formed, and then consumed. We are going to call that an intermediate. Okay. NO2, N2O2 is the intermediate because it forms and then it decomposes when reacting with O2 into NO2. Molecularity. Molecularity is how many reaction or how many molecules are reacting in an elementary step. How many molecules are reacting in an elementary step? And the idea is this. So imagine I gave 2 of you a bucket of baseballs or something. Okay. So first of all, unimolecular. Yeah, absolutely. That's going to happen because if it wants to break down and form some product, it can. And its rate law is equal to K times concentration of A. If I gave you guys some baseballs and I set 2 of you 30 yards apart, and I said, all right, I want you to basically make contact with these in the middle of the field. You could do that. I mean, maybe not all that frequently, but it would be easy for you to just make connections. And that's the collision would equal a reaction. So that would be bimolecular, 2 things hitting one another. So AA, that is the rate law for that. A plus B gives you that rate law. Fair enough. Termolecular reactions. Termolecular reaction would be, in order for a termolecular reaction to occur, is I would take 3 of you and you would have to have all 3 of your baseballs or whatever balls you have in order to connect at the exact same time. That is a termolecular reaction. The likelihood of 3, in this analogy, 3 baseballs actually making contact at the exact same moment, like all 3 of them touching each other at the same time, that's very difficult. So if you have only bi and unimolecular, these are valid, meaning termolecular reactions are invalid. So anything that contains an elementary step with a termolecular reaction is immediately regarded as impossible to do. Okay, so if we go back and we look at our 2 options, is it a 1-step process? Well, No, it's not. It's not a one-step process because it can't be a one-step process because it has three things. This would be termolecular. So that makes it invalid. Okay. But step one, that's okay because that's NO plus NO, that's bimolecular. N2 plus O2 yields bimolecular. So both of those check out. That is okay in terms of molecularity. So they have all of your single steps have to be uni or bimolecular. All right, last little bit. In a multi-step process, the rate determining step has to be, again, let's talk about what rate determining step is. So we've got two toll plazas here. Which one is going to, so these cars are slowed at toll plaza A and fly through toll plaza B. So this is really the one that is going to limit the speed at which a reaction actually occurs, because it is a slow first step and a fast second step, versus the other one, which is this is fast and this is slow. So there's two situations that we're going to run into. If the first one step is slow, that's the rate determining step. The second one is fast. And what that usually means is we can ignore the second step. This is easy. In the case where we have a fast first step and a slow second step, that's the rate determining step. This is harder. It's actually not that bad, but that is technically harder because we have to take into account the first hump as well as the second. Okay, so a slow initial first step. So I'm going to do this. Actually, we're going to kind of do this all in, we're going to do this in class together. So just bring this and we'll talk about how we determine the rate determining steps. And we have a bunch of these to do to get through and propose whether they're valid mechanisms. And then the final thing, let me just talk about catalysis. So we'll work on all of those in class together. Let's talk about catalysis. Catalysis is always faster because it has lowered the activation energy. So we have a lowered activation energy. And typically we have a different path. A different path, which leads us to that. Okay, so this is a catalyst, a catalyzed versus uncatalyzed reaction. Turns out lowering the activation energy rapidly increases the reaction. Okay, so again, the idea of a catalyst is here's the bromine, right? Here's the H plus, here's the H plus. So the HBr is not consumed. It can continue to process through the reaction. Right, Boltzmann distribution, again, if we want to run things at a lower temperature, and a catalyst might be the only way to achieve that, right? Because lowering the activation energy is basically saying, all right, well, if we add a catalyst, we actually can move it back here. That's the catalyzed activation energy, which means that now all of this stuff is reacting as well because it was catalyzed. And there are two different types of catalysts. Homogeneous, again, homogeneous is the catalyst in the same phase. I think in the lab we use copper is dissolved in aqueous, so copper with the reaction, the clock reaction to form the black stuff, right? So the copper is already dissolved, so it's doing its thing. Heterogeneous is going to be they're in the different phase. So the catalytic converter in your car is solid and the gases pass through it. And in fact, that's kind of, and this right here is the catalytic hydrogenation. So you're adding hydrogens because the things connect on a metal surface. So it's much more complex, but these are much more, I don't want to say stable, but they're much easier to kind of clean and to have available. But they're not as effective as homogeneous catalysts. They're the better ones. Homogeneous catalysts can fall apart. That's the problem. All right, good. So we'll go through those in class, and that is the end of the chapter. Quick and easy.